Yeah, the other method is the so-called shell method. And that's what this little handout has provided. It took me probably longer than it should. Actually, that was the hardest one to draw, so I figured I'd give you guys a break and not have you trying to sketch that as we go along here. But yeah, this handout, what I'm trying to show here is a little bit about what is called the shell method. Huh? No, just the X. I mean, we're just rotating about the Y. Really, though, probably what I should have go through with you first is think about this one. Let's say I have Y equals 2x squared minus x cubed. Okay? Y equals 2x minus x cubed. Matter of fact, let me kill that for just a second. All right, yeah, let's talk about y equals 2x squared minus x cubed. If I rotate that and y equals 0, if I rotate that region bounded by those about the y-axis, okay, 2x minus x cubed, I believe, doesn't it look like this? And y equals 0, so I'm rotating this region about the y-axis. Because if I rotate about the x-axis, that'd be a whole other story. But if I rotate that about the about the y-axis, isn't that the picture, what it looks like? Okay. So 2x squared minus x cubed, y equals 0. If I rotate that region about the y-axis, if I'm going to use the disk method, remember on the disk method, the rectangles run perpendicular to the axis of rotation. So if I use the disk method here, which way am I going to have to integrate with respect to y? Aren't I? Because here's my axis of rotation. If I'm going perpendicular to that, I'm going to have to integrate with respect to y. Which, do you see a slight problem there? I could use the right squared minus the left squared, but I have a slight problem because the function is itself. It's on both sides. I'm not going between this function and then another function. I'm going from this function to itself. That's a problem, okay? How are you going to do that? Well, I mean, I guess there's ways you could, but we don't want to do that. We don't want to even try to think about doing that. No, we're not going to use this method. That's where shell method comes in handy. Cue the handout. Okay, so shell method. Looking at the handout now, and this is the new function. We'll get back to that one in just a second. What we're going to do is, we're going to take this function of x equation, y equals f of x, rotate it about the y-axis, which is different because the f of x functions, remember, I rotate about the x-axis when I use this method. But with shell method, the y equals f of x, we rotate about the, but we'll get to that. And this is my attempt at drawing what it looks like. It's kind of a bell shape. It's got a hole in the middle of it, right? If I rotate that about the y-axis, I should get something vaguely resembling that, okay? All right. Well, shell method, the reason it's different is because now, if you look at it, if I take my approximating rectangles, I am going to take them vertical. So I'm integrating with respect to x, right? Delta x and dx. So I'm integrating with respect to x. And then I rotate those about the y-axis. Well, this is the reason they sometimes draw half shells is because they're a lot easier than drawing the whole shells, I assure you, for me anyway. So here's the half shell. So if I rotate this rectangle around halfway, this is kind of what it looks like, and then go the full way around. Yeah, what you get are shells instead of discs. See that? I get what they call shells. Tubes, I guess is another way you could put it. Right here?
Yeah, that looks like the function. What did that last shell have?
This shell, so I've got 3 shells. Here's shell 1, here's shell 2, and here's shell 3. That comes from these 3 pieces, rotating. So I've got this one, then I've got the one here, taking this one around. Maybe it's not quite high enough, but yeah, so that's shell 1, 2, and 3 to go with 1, 2, and 3. Is that what? Question? Okay. Yeah, so you get a tall one. This is the tall shell, the medium shell, and the baby shell. Okay? All right. So that's what you get. Now, what I'd point out here is, doesn't this do a fairly good job of that, approximating that? It does a pretty good job because, you know, you don't have the nice curves, but it does get some sort of idea of what the volume of this somewhat approximates the volume of that. That's the idea. Okay? So if I find the volume of each one of these, add it together, that's going to give me an approximation of the volume of the bell. Okay? But it's shells. I guess the thinking is it's, you know, kind of shells stacked together or stacked alongside of each other. But that's what they call it. All right? So we are integrating here with respect to x, but notice we're rotating about the y-axis. Okay. So if I take that middle shell there, if I take the middle shell from the handout there, here's what it looks like, right? It's kind of that long tube. And we could do it with the middle shell, and I mean the second and the third one too. But what I'm going to do is look at some things here. And this, you kind of have to refer back to that picture. Maybe I should leave that up there where we can see it a little bit. All right. So what is, because what I'm going to do is take this shell and unroll it. Okay? So what I need to know is, because when I unroll it, it's just a rectangle. If I cut this shell open, lay it out flat, it just turns into a box, basically a solid box, so I can do my length, width, and height. Okay? Well, here's the thing. Let's go with the height first. That's the easy one. What is this measurement on this rolled out shell? That's the function value. Okay? And I've got, you know, each one of these, x1, x2, x3, so forth. I did it with right hand, so it's f of x1. But if I'm doing midpoints, if I'm doing left endpoint, so let's just call that the function value at whatever sample point you want. And this one is x1, but in general, it'd just be f of xi, or f of x sub I star, depending upon, you know, midpoint, right endpoint, left endpoint. You see what I'm saying? Okay. But it is the function value. The height of this is the height of this, which is the function value. Okay? Everybody with me on that? All right. What about the width? Well, the width comes from this, doesn't it? Which is this. Yeah, delta x. That's delta x. So this is delta x. It's just the change in x. It's whatever we pick. We want 3 rectangles. We want 4 rectangles. Whatever it is. Okay? That length is whatever delta x is. The little harder one is the length here. We've got the height. We've got the width. What about the length? Well, if you think about it, we're going around. Basically, what it amounts to is this is kind of the circumference, the middle, if you will, circumference, middle ground circumference of that shell. No. We'll talk about, no, your limits of integration will just be A to B. Just going A to B. But it's like a circumference here. This length here is the circumference of a circular shape. Kind of the middle ground. I mean, yeah. We've made these shells pretty wide, but in actuality, if we were going to approximate, we'd probably get thinner rectangles. So it's more like more circular, but this is kind of exaggerated wide. But this is circular. So it's pi, or 2 pi times the radius, right? Two pi times the radius, which, what would the radius be? Well, that's kind of where, like I said, your shells are, your radius, if you think about it, is going from here. If we go kind of the middle, or, well, I guess, depending on your x sub I, or which endpoint or sample point you use.
That's what I'm asking.
Yeah.
The inside, outside, middle point.
Yeah. Let's just go with the sample point. If we're using right endpoints, it'd be the right outside point. It's the x value, right? Basically it. So, here we go. Here is our shape. So what's the volume of this? Well, it's just length times width times height. Yeah, let's go it this way. It's 2 pi xi star times f of x sub I star times delta x. Almost got it on there. Right? Length times height times width, I guess is the way I went, but to put it in the order that we shall see it. Okay? So that's the volume of this, which is the volume of that, which is the middle one here. What would the second one be? Well, it'd be similar. You just have the x sub I would change, be x2. So the sum of these three things, this would represent basically all three of those. So add all three of those up, and you approximate the volume of our original shape there. Okay, so each shell, basically this represents each shell. This is the volume of each shell. Okay? All right. Out of room. Let me just scroll up a little bit. I may want to come back to that. Okay. So each shell is this. So the volume of that bell shape is approximately the sum of three of those, right? I equals 1 to 3. 2 pi x sub I star times f of x sub I star delta x. Okay. All right. Well, how could it get better? Well, I could say make it 10 rectangles, make it 20 approximating rectangles, make it 50 approximating, make it 1,000. That would get them real thin there, really good approximate. However, the best way to do it is to get the exact volume is let n run to infinity, right? Whoops, I don't know where that extra sum came from. But if we do that, what is this? That's an integral, isn't it? We're talking about an integral. The volume is, this stuff just turns into the integral. It's the integral, a to b, of 2 pi x, f of x dx, isn't it? 2 pi x, f of x dx. That is called the shell method. And it finds, that one right there, finds the volume of the solid obtained by rotating y equals f of x, basically from x equals a to b, about the y-axis. What's the difference between it and the disk method as far as the formula goes? You have 2 pi instead of pi. Yeah, you got a 2 in front of the pi. And you don't have f of x squared. Have an extra x. Yeah. So it's not f of x squared, it's just f of x, but you have an extra x. And it's whatever the function is, yeah, you'll have that extra x. It's 2 pi x times f of x dx. That's the shell method. Now, the other thing to note there is that, again, I'm stressing this.
F of x is rotating around the y-axis.
Uh-huh.
Or we can do an f of x rotating around the x-axis.
Yep. We've noted here a couple of times that in the disk method, the rectangles run perpendicular to the axis of rotation. Here, the rectangles are parallel to the axis of rotation, aren't they? So that's kind of the key ingredient on the shell method is that, get rid of that. On the shell method, the rectangles, approximating rectangles, are parallel to the axis of rotation. So if you're trying to decide, do I want shell method or disk method, that's how you do it. If you want to do dx and you're parallel to the axis of rotation, that's shell method. If you're perpendicular to the axis of rotation with dx, that's the way you want to do it. That's disk method. Okay?